discussed in the last class. So, what are the topics we have discussed in the last class? Just brief me what you learn. So, just tell me what is the use of checksum, what is the use of ECC, and then how you calculate the ECC and how you calculate the checksum. Mm-hmm. Now today we will discuss about LRTE link latency reduction and transport efficiency. So what is that? Latency reduction and transport efficiency, how we are calculating. Okay. So latency reduction means what? Now is Vishwin, right? Just what is that latency reduction? Latency reduction means, see, camera is transferring the images or videos or anything from the transmitter side to receiver side. So from the camera to processor, we are transferring the images, right? So that images. One image you transferred, you send it means the next image we need to. Yeah, hello, voice is breaking. Okay, just inform. Now, okay, okay, fine. Okay, so here latency reduction and transport efficiency is a feature of MIPI CSI-2. What is the use of that means it reduces the unnecessary pauses, right? See how the train is super fast train is moving, right? So it is going 100 kilometers per hour. It is moving from one station to another station. That's why the small stations, what are the small stations are there, that is not stopped, that is skipping, right? Because of fast transmission of information. Same thing here also, the camera is transferring the fastest information from camera to processor. So this LRTE will reduces that unnecessary passes for continuous transmission of information, right? So that is the main usage of LRTE we are using, link latency reduction and transport efficiency. So that transport efficiency is having the problems like when the packet, yeah, when the packet is finishes, or when you are sending one packet, after that it is reaches to LPS state, that means idle state is going down, and then another transition will be happening after coming out from the LPS state to high speed state. Okay, so this will be reduced by using LRTE method. Okay, so all these are happening. Then what is the problem we are facing? So these are facing means will reduces the time. Okay, time will be reduced, and then power is also reduced. After that means power is also consumed, and then bandwidth efficiency also reduced, right? So that will be wasted. Okay, whatever the bandwidth we are using, so unnecessarily we are pausing means, that means we need to check properly. Suppose one lane is just assume that metro train. Okay, you are going to the metro station, one person entering into that metro station, he's checking that, he's checking, and then we are collecting the bag, all these things, it will be taking some time. Okay, that time is wasted. So 1 minute or 2 minutes is wasted. Same thing here also, when one packet is transferred, okay, while transferring the next packet, we are uh, we are going to that LPS state, low power state is going on that state to, again you are going to the high power state. Yeah, tell me. Hello, hello. Tell me, Ramya. So hello. Yeah, audible. Hmm, hmm, fine. So latency reduction and then transport efficiency, why we are using means to reduce the to reduce the unnecessary pauses in our packet. We are going for latency reduction and transport efficiency. So here, why we go for what it is doing that? What problem is that trying to resolve this LRTE means how packet is finishes and when it is finishes the packet, that will that after that, whenever it is entering into the low power state, we need to identify that it is going to the low power state. We need to identify LRT will be identify that. And another transition, when the another transition will happens, when the other packet will be transmitted. So from transmitter side to receiver side, that will be taken care by the LRT. And then it is also used to uh, reduce the how time is wasting, and then how much power is wasting, and then how the bandwidth is utilized. So it will reduces this power, and then time, and then bandwidth. All these three things is that wasted means, so it will be taking care of that without wasting the time, power, and then bandwidth. So it is used to transmit the information. When these issues will be coming means, so large information you are transferring, from the transmitter side to receiver side. So this will be causing that. That means high frame rate you are transferring. So that means large image you are transferring from one camera to processor. At that time we will face this issue. Okay, so there are two types of two parts of LRT is there. In that, one is interpacket latency reduction (ILR). Interpacket latency reduction (ILR). What is that interpacket latency reduction? So it instead of stopping and then going to the stop, so suppose your your shut down your system, right? At that time, it will be going to the sleep mode, and then again you going to restart. All these things we are doing that. So same thing will be reduced by this interpacket latency. So it reduces the packet delays between the one packet to another packet. Suppose one packet I am transferring, another packet is also transferring. In between that, there is a delay. That delay will be reduces. That is the interpacket delay. Okay, interpacket latency. Okay, so interpacket latency, and then how that efficient packet delimiter is working that. And then there is another topic law called enhanced transport efficiency. How it will be improved that bandwidth, it will be taking care of that. Okay, so reduce the interpacket delay. So how it is reducing the interpacket delay means efficient higher effective data rate throughput from that high speed to low power state, and then low power to high power state, it will be reduces that. So that is the interpacket latency. Okay, interpacket latency, or interpacket reduction, interpacket latency reduction. Clear? What is that Yeah, yeah. Mm. Interpacket latency is used. Interpacket latency reduction means, so suppose you are sending one packet of information. Okay, so now audible. Just LRTE is used to reduce the reduction bandwidth, and then power consumption, time consuming. All these things will be reduced. Okay, so that is so. Bandwidth waste, actually wastage of time. Okay, so wastage of time is wastage of time is reduced, and the wastage of bandwidth is reduced. That means See, you're transferring long packet of information and then end of transmission. After that, LPS state and then start of transmission. Again, start short packet and then end of transmission. See, this LPS is the low power state, that is idle state, not doing anything, right? So this LPS state will be reducing. So we are reducing the low power state because while transferring the information, it is in high speed state. Okay, so this high speed state to we are going to LPS state, that is low power state. So again you are transferring the another information, means you need to go to that other transmission, that means other packet you need to transfer. At that time, from LPS state to high power state we need to switch, right? So then this LPS state will be reduced by this interpacket latency. Okay, latency reduction. What it is doing, that interpacket latency reduction means it will reduces the stop condition, and then it will reduces the delay between the packet 1 and packet 2. So for that purpose we are using this packet 1 and then another packet 2 we are transferring. In between that low power state is there. This time is reduced by interpacket delay reduction or interpacket latency reduction, ILR. Okay, now it's clear. See, this is the ILR is that how it is transferring the information, means there is a long packet format. In between that, end of transmission is there. So this end of transmission means where you are stopping the frames, where we are stopping the data, and then LPS state means it is an idle state. Again, you are going to start of transmission. Okay, so this start of transmission, all these three will be reduced, and then one packet is introduced, that is the EPD, Efficient Packet Delimiter. Okay, LRTE with EPD, Efficient Packet Delimiter will reduces that. What it is reducing? End of transmission, LPS state, and start of transmission. So all these three things will be comes into one rate, that is that EPD. Okay, EPD will replaces the all these three things, end of transmission and then LPS and start of transmission. Now it is transferring the data like long packet, EPD, short packet, EPD, long packet, EPD, and then short packet. Okay, all these three things are replaced by single EPD. Then it will reduces some time, right? Yeah. So that is the reason. See, that is the reason we are going for EPD, LRTE with EPD. That means one packet you are transferring, in between that EPD is there, other packet you are transferring. Okay, so next packet we are transferring. Why this EPD is uses? So this physical layer, whatever the C5 layer or D5 layer you are using, that will be in active position. Okay, so that C5 layer or E5, D5 layer you are using, this 5 layer we are using, right? So where is that? Hmm. So this 5 layer we are using, C5 layer or D5 layer we are using. This 5 layer still in active region, so it will be helping, that EPD will be helping to stay on active region only. Okay, and then this EPD will also reduces that, not switching to high speed to low speed. Okay, high speed to low speed, low power switching, low power state we are not moving that. This is also eliminating, and there is no restart. That means again your LPS state to high speed state you are going, that restart will be not there. Okay, so this EPD will reduces that, and also reduces the synchronization delay. Okay, synchronization delay means one packet to another packet you are transferring, means so that synchronization delay will be reduces. Okay, so that is the LRTE. So link latency reduction and transport efficiency. Okay, so how this EPD legacy packet flow. So this legacy packet flow, you know, right? So how it is transferring the data: short packet, packet header and data, packet footer, end of transmission, and LPS. See, you know that what is the meaning of packet header? Packet header is it will tells you what type of data you are transferring, right? So that packet header is that terminology you are using, and then start of transmission. You know that where you are starting the data. That means when you are transferring the data, all these things. And then LRTE with packet flow, how the packet flow is transferring that packet header and then data. So packet header, data, packet footer, EPD, and packet header. Again, data you are transferring. In this way, we are transferring the data, right? So packet header, data, packet footer, and of transmission. That is the long packet and short packet methods. And then this data will be transferred with LRTE packet flow. Okay. So what is that? It is reaching from high speed to low power state and then low power state to high speed state means. So high speed is the one mode, that is the data transfer mode we are using, and LPS is the low power state, that means idle state we are in there, and then again we are switching from high speed state, that high speed state. This cycle, so whatever the transition is happening, this will cause that clock cycles increases, and then synchronous time is also increases, and then energy is also increases. So all these things are removed by this LRTE. Okay, LRTE will remove that one. And how the C5 will be taking care of the data. See, C5 is that another C5 is a layer in MIP, we are using the MIPI, right? How many layers how many lanes we are going through, the data is transmitted in C5 layer. In C5 layer, three trios are used, right? Three trios are used. It will increase the higher efficiency and then reduces the number of wires, yeah, number of wires used in that data, because here, yeah, data as well as clock will be transmitted embedded way. Okay, that's why it is reduces the data, so it which reduces the wires count. And it is also having like packet delimiter quick, so PDQ is called as packet delimiter quick. What is the use of this packet delimiter quick means? It generates some user interface sync words. Okay, so while transferring, while going to the file layer, it will generate that user interface, some user interface sync words. Like in between the data, you are sending the data, sync word is there. This sync word, what is the use of the sync word? It will like a spacer word, right? Yeah, it will. It will stops the delay and then rearranging the words while retransmitting the information from the transmitter side to receiver side. All these things are taken care by this spacer word. Okay. So how the register will be configured means, so register configuration means, so he see here some spacer word spacer optimal spacer word is there, and then PDQ packet delimiter queue is there, and then next packet we are transferring. So the registers, how the registers is transmitted means, it is transmitted like 16-bit word. The data width is 16-bit word. Like EPD enables that short packet method and then long packet method. So that will be transmitted to 16-bit. That means 2 bytes of data you are transferring, right? 2 bytes of data you are transferring from one transmission side, like transmit register CSI EPD layer is there. That way, in that way, the data will be transmitted. If it is 0 means it will be work as a spacer. If it is 5 means or 1, it will be work as a 5 spacer words. Okay, 0 means there is no space. Okay, so no spacer is there, and then 5 means it will be 5 spacer word, and then it is reaches to up to what is the length means 3 to 7 6 7. 3 to 7 6 7 is the maximum spacer we are having. Okay, that will be supported by the registers. And D5 is also EPDs. Sorry, spacers means data in between the data we are having sync word. Okay, so that is the spacer. So that spacer is supporting that how many packets it will be sending means zero packets to, okay, it is sending 0 to 3 to 6767, okay, zero packets to 3 to 767 capability of data packets is transmitting. Yeah. So that is the most capability of data transmission. See, I told you right. We are having the zero means no spacer is there, and five means five spacer words are there. So that is 5 into 7 user interface data we are transferring. Okay, and then decimal 32767 means so 32,767 word spaces will be transmitting. Okay. And then D5 layer we are using that it is an optional like EPD layer is an optional. Okay. And in this option like D5 layer we are having different type of options like D5 with EPD option 1. So this option 1 is recommended way we are transmitting the data. So in this recommended way we are transmitting the data. How we are transferring the data means packet 1 and spacer byte and again PDQ, after that packet 2 you are transferring. That means best lane alignment will be taking place here. Okay, so lane alignment means we are transferring the data through multiple lanes like lane 0, lane 1. Okay, so in that lane 0 and lane 1 we are transferring the data like data 1 to n number of data we are transferring. And then packet spacer all the data will be reaches to FF means because it supports that 16 bit, right? 16 bit means 00 to FF it is transferring. So FF it is reaches means there is no space, right? So last value is reached. This last value is reached means there is no space in between the data n to the next data we are transferring, right? Packet delimiter queue is there, right? So that packet delimiter queue in between that there is no space is placing. That means blanking is not allowed here. Okay, one packet to another packet, this packet delimiter queue is taking place, it will reduces the space. Okay, and then option 2 is also there, that is legacy compatibility. This legacy compatibility there is no PDQ here, PDQ is there and there is no PDQ, only spacer only there in between the lane data 1 to n, and then start of transmission is there, next packet is transmitting means, so in between that PDQ will be eliminated. That PDQ will be eliminated means so the compatibility with the older system is easier. Okay, if no PDQ is there means whatever the previous sections we are introducing that compatibility will be easier. And then here lower alignment quality, that means PDQ is not there means whatever the data you are transferring from the transmitting side to receiver side, okay, that alignment will be missing here. Okay, and it is also supporting that alternative low power states. Alternative low power state means it will also supports that LVPS low voltage and then low power states. So LVLPS means low voltage low power state will supports means it is never going to that idle state. Okay, while going to the idle state it loses your power, right? That means see your starting the engine and then stopping the engine. So starting engine and then keep on starting means there's less power, less petrol will be consumed. And then again you are starting and then stopping means so fuel consumption is more. That is the reason we are going to alternative low power states we are using. This alternative low power states will reduce the low latency power. Okay, lower latency, that means delay will be reduced as well as power consumption is also reduced. Okay, so that means whatever the interface you are using, that will be keep on in active state only. Okay, your laptop is never going to that idle state or sleep mode. It will be instead of your shutting down, it will be in active state only. Okay, clear. So this is the start of packet data, end of transmission, and then low power state and start of transmission. This way we are transferring the information. Priyanka, are you there? Okay, okay. Yeah, yeah, audible, audible. Are you understood what I am explaining for link rate transport efficiency? Hmm. Ah, okay, okay, fine. Okay. So data scrambling, what is the reason we are going for the data scrambling? Yeah. So data scrambling means, suppose I'm talking continuously. So that data will be different data you are transferring, right? Every time you are talking means different data you are transferring, but every time on shouting means same data will be transferring, right? So same data, repeated data, shouting means same sound will be reduced. That means noise only we are transferring. That noise is happening. Yeah, repeated data you are transferring. That means suppose your repeated data means, suppose packet 1 only, this packet 1 only we are transferring. That gives you that some interference, if interference is happening. That means some echoes are transferring. That echo is repeating means we are losing our data. Okay, so that's why we are sending different data randomly. So random words we are transferring means, okay, different data are transferring from one transmitter side to receiver side. Okay, so that is what scrambling, data scrambling is the technique. What is the technique we are using means, we are randomizing the transmitted data. Whatever the data we are using, transmitted data we are using, that data will be randomizing. Because it will when you are transferring the data, randomized data you are transferring, that will reduces the EMI. That means electromagnetic interference will be reduces, and whatever the signals are transferring, the signal integrity will be improved. Okay, signal integrity will be improved, and it will prevent that repeating of data. So repetition of data, see, p1 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 p1, this p1 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 will be transmitting twice, many times. That means we are losing our data. Okay, so whatever the input data we are transferring, so input data and then scrambler, the input data and scrambler and randomized data we are transferring through some file layer. Okay, so in this way we are transferring means whatever the actual information is there, that data will be appeared at the receiver side. Okay, so that is the most of the cases we are transferring the data by using scrambler. Without scrambler means our camera is taking too longer time to capture the pixels, and then repeated zeros or repeated ones only transmitting, so that will loses our data. Okay, so that should be avoided by using the scrambling. Okay, yeah. So how this EMI reduces means unwanted electromagnetic radiation, right? So electromagnetic radiation. That is electromagnetic radiation means you are sending same data means that interference will be causing. That interference will be reduced by using this scrambler. Okay. So by increasing that different wider range of frequencies we are using, so that wider range of frequencies will be allowing to improve the channel efficiency. Okay. Yeah. Tell me. Yeah. Hmm. 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 We don't. we don't know. See, we lost that data transmission means. So suppose you are transferring parallel scrambling. In that one data you are receiving, right? Same data. Suppose we are copying one data and transmitting the other data. That copying is same data. Sometimes we are copying, right? So sometimes we are copying one image. It is copying that one image. That copying and then transmitting to processor. Okay, it will be processing. Same time, another data is also transferring instead of that previous copy only transferring. That means the copying is not happening properly. That time the repeated data will be transmitted. Or some noisy channel is there. In that noisy channel, so you are transferring one packet, that packet is not received by the receiver. Again you are retransmitting the same packet, right? Yeah. Again, you are retransmitting the another packet like packet one only. So that is the repeated data you are transferring. So that is reduces by this scrambling. Okay. So how this parallel data will be splitting the data means you are having lane 1, lane 2, lane 3 and lane 4. So how these lanes are divided, suppose you are traveling on a highway, so you got the one toll gate means one lane is related to trucks and other lane is related to bikes and other lane is related to cars and other lane is related to some halt we are having, right? So each lane is having different data, but all are pass this toll gate and then reach to their destination. But they are reaching at different intervals of time. Okay, so this scrambling will introduce that pseudo random bit sequential bits will be introducing. So PRBS, so pseudo random bit sequence. So this pseudo random bit sequence will be generating proper data and then aligning that each and every data at the reconstructing at the receiver side, it will be reconstructed and then it is sending to the processor in an order rate. Okay, that is the purpose of PRBS. Then scrambler is introduced that LFSR or PRBS. PRBS is the pseudo random bit sequence. Sequential bits are transferring. Okay. Mm. It will do that XOR operation. If that XOR operation is doing that, see all the bits are doing the XOR operation. All the bits are doing the XOR operation. You will get all zeros means there is no error in your data. If you are getting some error means you need to retransmit the data or you need to check the data which type of data you are transferring. Okay, this pseudo random binary sequence will check that. Yeah, tell me. Ah. See, data compares all zeros means you will get the zero only. That means that is the repeated data, right? So that is the problem we are facing with this scrambling. This scrambling. So you are sending. See, all the data are same means what is the need? So that's why noisy data only transmitting. That's why we are using rand. Uh, hmm, 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 hmm. Uh, Yeah, this will best image having different value, highest image having different value, and then video is having different value, each and everything having different values. Suppose you are transferring the data like 1980 divided by 1090, this resolution you are transferring. Okay, suppose 1982 divided by 1090 resolution image you are transferring. That means this is the high quality image. And then other image like some 420 by 840 resolution you are transferring, this is lowest image quality. These having the different pixels data, this will take different lines of data and this will take different lines of data. So different images, different transmission. Every time you are transferring the data from through your WhatsApp, okay, you are selecting different images. In that different images, we are having high quality data is there, low quality image also there, each and everything having different values. So at that time we are data will be mixing way or shuffling way we are transferring. That means whatever the first image you are transferring, we don't know. That will be taken care by this scrambler. It will be ordering and then reconstruct the original image. So and it will transfer the data, because one line you are transferring one pixel. So these many lines we are transferring, 1980 lines we are transferring. Okay, so one line eight one pixel in one line, these many bytes of data you are transferring. Suppose what to nearly it is reaches to 2400 bytes of data. In this 2400 bytes of data, all the bytes of data will be having valid data or invalid data, we don't know. Okay, so that's why in this one line, the pixel data is the high quality image or low quality image, we don't know. So that's why it is taking different data, not having the same data. See, this is my frame. In this frame, different lines of data we are transferring. So these different lines of data, each and every pixel having different values, right? One pixel, but bytes of data is common. Every time 2400 bytes of data you are transferring, but their content is different, right? So because in the frame one image is there, that image at one place high quality image is there, and another place low quality pixels are there, and another place still low quality pixels are there. But each lane or each image or one single image, different pixels are there. That's why we are sending different data, randomized data we are sending. Okay, or you are not randomizing the data, same data will be repeating. That same data will be repeating means, so one eye only it is visible at the, say, you are capturing the image, the children is capturing the image means they are not capturing the full image. So they captured the legs, or they captured that body, or they captured the head, or sometimes one single hand they are capturing. That will be happening, right? Yeah. So that's why we are randomizing the data, and then scrambling will be taking care of that. That will be any repetition of data is there means that will be randomizing, different data will be transferring. That at the end it will be reconstructing the whole data. Okay. Yeah. So here D5 scrambling is there and C5 scrambling is there. In the D5 scrambling, what we are taking, the leftmost diagram is the D5 scrambling. So zero states is there, high speed zero state, and then high speed tail is there. That zero state means starting of the transmission and then ending of the transmission. Okay, so it is also syncing for the high speed sync is there. High speed sync means, see, multiple lanes are there, multiple lanes in that we are initializing that different packets of data, byte 0, byte 2, byte 0, byte 2. See why we are transferring the data in the byte 0, byte 2. One lane I'm transferring the event pixels or event data, and the other lane I'm transferring the odd pixels or odd data or odd packets I'm transferring. Okay, see, that is the DeFi layer. We are seeding that different type of data. Okay, that different type of data having different images. Like even data is having different pixels, and odd data is having different pixels. Okay, same way C5 is also used to transmit the data from the transmitter side to receiver side. Here also we are transferring the data like packet data P2, B0, B1, B4, B5. See, B0, B1 is the alternative way we are transferring that. B0, B1 is the one packet, that is 16 bits we are transferring, right? B0, B1, byte 1, byte 0, byte 1, and then byte 2, byte 3, again byte 4, byte 5, and byte, yeah, Tell me. Hmm. 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 Seed 0, seed 1, seed 2, seed 3 is there, right? Ah. Hmm. 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 8421 code is there. Hmm. Okay. Okay. Ah. Even. Odd. Hmm. Hmm. No, so we are not calculating based on the 8421 code. So here we have the pixel images like what is the pixel data, that means image resolution. Depends upon the image resolution, we are transferring the data. Depends upon the image resolution, we are transferring. Suppose 91980 is the image resolution of the horizontal lanes, and then vertical lanes are also there, and then 1080 is the vertical lanes. So these many lines I need to transmit to complete one image transmitted successfully, right? So then this 1980 bytes I need to transfer per lane. One lane I need to transfer 1980 bytes of data. Okay, that means 1980 bytes of data means we are having byte 0, byte 1, byte 2, and so on, so up to byte 1980. Okay, so this 1980, yeah, so here we are having even bytes and odd number of bytes. In the D5 layer, it is transmitting like, yeah, yeah. So no, don't use that data. This byte is having different bytes of data like 0101, 1010, whatever it the data contains, I don't know. See here, different datas are there. See, DEEEF and then D5A3 and then ACE1. Different datas are there. This is related to seed 0, seed 1, seed 2, and seed 3. This seed 1, seed 2, seed 3, 16 bits of data is transferring. That data maybe is a different data. I don't know what type of data is transferring. Okay. So depends upon the pixels, it will be taking care of that. Okay. Same way C5 is also having differently transferring the data from packet preamble, and then different bytes of data. Sync header is also there, packet header, and then packet 1, packet 2, packet 3, and then word 0, word 1, word 2. That means 16 bytes of data, 16 bits of data you are transferring. Okay. So anything else here? That is the scrambling versus what about that PRBS? Okay. So up to this you can take care of that packet data and payload size rules we can taking we will explain by tomorrow. So already 8 o'clock is completed. So I think Priyanka is not participated today well in the class.